You'll see that this level is labeled level 1. The one down below us is labeled level 0. It's important for us that we are operating the experiment the way that we think we should. Okay? So we have a full quality assurance program. And if you think through all of the kinds of mistakes you can make that you want to minimize the frequency of, one obvious type of mistake is that you could have a valve in the wrong position. It could be closed when it was supposed to be opened. And if you've done that, then the system is not going to behave the way that you expect it to. So to perform experiments, it's important for us to verify that all of the valves are in the positions that we want to have them in for that particular experiment. And therefore, we label levels and we have tables. And the students, in starting up and running through their detailed procedure for an experiment, will systematically go valve by valve to confirm that it's in the correct position. Then as they evolve through the experiment, if there's valves that need to be repositioned, for example, we have a full fill-up procedure and we don't want to overflow things and such. And so as you're filling to certain levels, you open and close valves. And again, this is all driven by procedure, and we document and then put that into a database so that we can verify that we really know how the experiment was run.
Has the facility been filled up yet?
The facility is full as we speak. We have been doing initial heated testing. We did isothermal testing to measure pressure drops. We're now in the phase of doing heated testing. Our next stage is actually going to be to come in with infrared camera, and while we've got the loop heated, we're going to be looking for all of the places, and there's going to be plenty of them, like these valves and stuff, where we're losing heat. And the next stage is going to be to come in and add additional insulation at those locations so we can bring the heat losses down further, because those actually represent distortions compared to what the prototypical full area system would look like.
And what is the general temperature range that the oil will go through as it goes through the loop?
Generally, we're going to be running at oil temperatures around 80 degrees centigrade, which is where we're pretty close to matching Flibe at about 650 degrees. Typical temperature drops in the PBFH are about 100 degrees from the core inlet to the outlet. And in the scaled world with oil, that translates to about 30 degrees delta T.
Okay, so 50 C to 80 C roughly.
Exactly. And what we'll do is, once we've minimized heat losses by using infrared imaging, we'll characterize and measure those heat losses, because when we run at a fixed flow rate with heat input, and we know what the flow rates are in different legs of the loop, we measure temperature drop between those positions and we can estimate the rate of heat loss. What we'd like to do is to make it small. The next stage is that we're going to be installing insulated shutter system that'll roll up and down on the front.
Oh, I see.
Because we're going to put a nice big electric heater in here, heat this up to be close to the oil temperature, then the temperature drop across the insulation drops further. This is called guard heating. And when you get the temperature drop on the insulation down, then your heat losses go down as well. And you further reduce the distortion in the experiment caused by having heat leaking out of the loop.
And that way it more closely matches the design of the system that you want to simulate.
Correct. Yeah, and that's what we'd like to do, is to get it to behave as close as possible to the actual physical system. And then we just run all sorts of different transients on it, including things that you wouldn't physically be able to want to or be able to do in the actual loop itself, or in an actual reactor itself.
So one of the things you mentioned earlier was this type of a simulated scaled experiment has been used to help license other reactors.
Yes. The very earliest light water reactors that were built did not have emergency core cooling systems. And when it was recognized that if you lost your ability to provide your normal cooling to the core, or if you had a loss of coolant accident where a pipe would break, that you could have very bad consequences of having fuel overheat, especially in light water reactors, because in light water reactors, if you allow fuel to be uncovered and you allow it to heat up, the cladding will react with steam to form hydrogen.
The zirconium cladding.
Yeah, the zirconium cladding. And as the fuel overheats to temperatures where it begins to lose its physical integrity and have localized melting, in the chemical conditions that you have with water, highly oxidized conditions, cesium and iodine are very volatile, and they evaporate out, form small, condense as small particles,
Aerosols.
and you have intrinsically high pressure, and so you therefore have physical mechanisms
Dispersion term.
that can mobilize cesium and iodine. Now, we designed the reactors to make that very unlikely. Through a combination of highly reliable cooling systems. Passive systems are better than active, as we learned at Fukushima.
But the physical mechanism remains.
The physical mechanism remains.
Whereas in a salt reactor,
cesium, there's nothing that cesium loves more than fluorine, and it will compete with anything else to grab a hold of fluorine. And cesium fluoride is very, very low volatility and very high solubility in salt.
so no aerosols. Doesn't want to form an aerosol, and,
Yeah.
and no driving term to make it want to get out.
Now, one of the key things for the solid fuel, cesium is locked up in the fuel for sure. Xenon, which you want to get out of the primary salt for your fuel salt, xenon decays to cesium. So the one thing we have to be cautious about with the fluid fuel and do it right is to make sure that the xenon decays and we get that cesium back into salt after the xenon decays. And this has to do with the off-gas system design, which of course you've looked at a lot and many others have as well.
Yeah, and I think one of the thoughts in that way was to use the drain tank, which had a certain amount of fuel salt in the bottom,
Anyhow,
as
right.
a logical place for that to take place.
And once the cesium is there, then subsequently to mobilize it in any type of accident would be extremely difficult to do. Right. So this is sort of an intermediate elevation. Of course, we've got two more up above us. At this point, there's not all that much that's exciting to point towards, except we do have here one of our sight glasses, and this is one of the things that we use both when we're filling to verify that we know what the level is, although we also see the level come up in the various different manometer lines, but also under forced circulation, we monitor this to make sure that we've gotten rid of all of the gas bubbles, right? Because there's a few high points here that collect it, although all the high points in the loop have vents to get the gas out. Okay, maybe we should go up one more.
One more.
Now we're coming up onto level 2, from level 0 and then level 1. We have the high point of the primary loop of the FHR. And so, in fact, you can see here the level indicator on the tank, right down here. And this is the top oil level in the loop, and you'll find various different places where you'll record the same level.
So if we could see through everything, we would see all the oil is at this level.
Right, and if you look over here, this is the first station where we do oil level in the manometer rack, right? And if you look carefully, if you get the light right, because that's transparent, our camera does a better job actually sometimes than the eye does. We'll be able to see, yes, right here, all of the orange manometer lines are primary. So these are the manometers that show pressures in the main part of the loop. And when we run the loop, what you'll observe is the oil levels will depart due to the pressure drops. We actually also can spot in these manometer lines the daily fluctuation in temperature in the room. Because some of these lines run all the way down to the bottom of the loop and they stay very close to the room temperature, air temperature. The ones that are in the insulated piping lag, and so day to night the temperature goes up and down in the room.
You'll see that effect here.
You'll see it, a millimeter or so of oil level difference.
That's interesting.
And of course in our calculations we take into account the actual temperature of these lines so that we can get the pressure to very, very accurate values. This fan cooler down here is the one that simulates the coiled tube air heaters that remove heat from the primary loop. And again, it's on a variable frequency drive. So we can control the speed, and we've shown that we can actually control to give a specific heat removal from that location at the correct elevation in the loop. This, you'll see, is the fourth Coriolis meter. And this is the one that is measuring the flow rate in the natural circulation decay heat removal loop, the Drax loop. If we go up one more level, we'll be able to see. And this is the camera that takes the data for the manometer, the first set of manometers. And of course, modern cameras are phenomenal. Watch your step coming up.
I see there's another camera there to take that level.
Exactly. And the blue manometer lines are the ones on the Drax loop. And you can actually see the oil levels in those lines over there because they reference over to the top head tank.
So that course, oh, so there's the same level in this
Yep.
pipe as well. Isn't that remarkable that no matter where it is, they're all at exactly the same level?
And now, because this is buoyantly driven, we'll see much smaller changes in height and in head. Now, another thing I'm going to talk to the students, because every now and then you'll find a gas bubble. This, you can see this was a bit of a challenging line because it is so close to being horizontal.
Yeah.
But keeping sure that we don't have bubbles in the system is something that we've learned a lot about here. And it's something you want to think about if you're designing a real reactor where you can't see the bubbles so easily.
Yeah.
This is the, again, variable speed drive fan oil cooler that allows us to mimic the heat removal that our coiled tube heat exchange, or our thermosiphon cooled heat exchanger would achieve to extract heat out of this loop and drive natural circulation. And the observation in our initial transients is that this thing loves to suck heat out of the loop. Now, the only other thing that I would point to is down there. You can see this valve right here. That's a needle valve, and by adjusting the position of that needle valve, we have the ability to adjust the amount of flow resistance in this loop. And of course, it's the balance between the flow losses and the buoyancy forces that determines the flow rate and determines the temperature difference. So we can actually adjust those losses in this loop across a wide range, and therefore we can simulate a wide range of different Drax designs with this one facility.
Well, this is really, really neat. Thank you for showing it to us.
Okay, you're welcome.
See if we can make our way down.
Okay. This is our fourth floor laboratory.
I can smell that smell now that I know what it is.
Yep, exactly. There's still some residuals around here because we ran our last set of Dowthorn experiments a few weeks ago, where we were doing heat transfer measurements in heated tube, as well as there's a small test section over here where we can do heat transfer measurements to and from packed bed of spheres, which gives us the ability to predict heat transfer coefficients from pebbles to salt for the pebble bed fluoride soap cooled high temperature reactor. This loop also allowed us to do heat transfer experiments, as I mentioned before, in heated tubes, and we can compare that heat transfer coefficient data to data for Flibe and show that they're very, very close. And then we also did natural circulation here and validated models for natural circulation because the heat removal from this loop is up at a high elevation, heat source is at a lower elevation, and we're able to generate natural and forced circulation flows and validate the relap models. We also have a series of experiments that we've been doing that relate to being able to use pebble fuel in a salt-cooled reactor. Now, pebble fuel was developed by the Germans back in the 60s and 70s for helium-cooled reactors. They went in the direction of pebble fuel. In the United States, we went towards fixed prismatic fuel. And so their designs, which have now been replicated in China, would circulate pebbles by adding pebbles to the top of a bed and removing them from the bottom of the core. And a typical pebble might go 8 times through the core before it reaches sufficient burnup that you'd replace it with a new pebble. Now, the key challenge that we were running into with trying to do solid fuel with molten salt coolant is the fact that graphite is less dense than salt and floats. And therefore, fuel elements want to float. And this is a real headache if you've got fixed solid fuel like plate or prismatic. In 2006, trying to figure out how to solve this problem for the fixed fuel designs that we were focused on, we realized that it might be an advantage that fuel floats if you have pebbles. Because in a salt-cooled reactor, you want to have the coolant in a vessel that has no openings around the bottom. That is a pool type of configuration, which means you don't want to take the fuel out from the bottom of the reactor, right?
You want to take it from the top.
You want to take it from the top.
And that works out well with pebbles.
And it works out really well. And so this experiment, what we did was we basically, as soon as we recognized that we wanted to understand whether we could circulate pebbles, we knew that we'd have to invert it because invert the helium design. And we already had been doing experiments where we're matching the fluid mechanics of Flibe using water. And if you scale to 40% geometric scale with water, you can match, with water, you can match the Froude number for the buoyancy related forces and the Reynolds number. So all we had to do was to find a 40% scaled pebble material that would have the right density ratio with water.
Polyethylene.
And
polypropylene?
Yes, no, high density polyethylene and polypropylene also works. I went home that evening and went to the kitchen and started taking out my wife's plastic stuff and cutting it up to see what would float. And after destroying a lot of perfectly good, plasticware, I finally got around to cutting up a milk jug.
This is science at work.
That says
science at work.
And the stuff floated. And then I looked on the bottom and I looked up the recycle number.
Yeah, I actually did the same thing when I was looking for the same thing.
High density polyethylene. I said, wow, okay. And within 10 minutes on the internet, I'd found vendors that would sell us these 1-inch diameter high density polyethylene spheres, and we bought 8 or 10,000 of them.
And if I'm not mistaken, polypropylene is even cheaper.
Yes, and moreover, when I'll show you in a moment, polypropylene is a little bit lower density, and so we've used it for instrumented pebbles where we're doing X-ray tomography for full beds now.
Oh, okay.
So at any rate, so this was the first experiment. It's what we call a wet PREX, pebble recirculation experiment. 8,300 pebbles when it was operating. Inject pebbles into the coolant line. They get carried in, deposit on the bottom, and then defuel by just scooping them out from the top. We then decided that to get to higher power density, since pumping power is so low with the salts, the huge volumetric heat capacity, we found that if we went down to 3 centimeter diameter instead of 6 centimeter, so the gas-cooled reactors use billiard ball size, went down to half that size, we could go to power densities 4 to 5 times higher than what you have in a helium-cooled reactor, vastly more compact. The fuel reaches full depletion much more rapidly, and the startup fissile is very similar to what you have in an MSR at these power densities, right? Because it's very similar power density to the fluid fuel, so very little fissile, about 1/3 the amount that you need to start up a light water reactor to get a solid fuel molten salt reactor to work, as with the fluid fuel. So as we went to the smaller pebbles, of course, we had to procure smaller pebbles. As you can see up there, those are 1/2-inch diameter.
So when I was here before, this was all filled up with the multicolored pebbles.
That's right, just like in the picture there.
So
And
that's what I saw when I was here.
Yeah. We've got all of the PREX experiments. You can see we've done a ton of them. This is dry. And this one is for a 900 megawatt core. It's a 15-degree segment, and at this point, as we go to large cores, the key thing is that we need a place to insert reactivity control elements, not in the outer radial graphite reflector, but on the inside one. And that's the reason that we've been looking at center reflectors as places to insert control elements. And we were able to demonstrate that we can generate radial zoning. Yeah. And also, you'll see that there's very interesting dynamics. So in this case, because it's dry, the pebbles are coming in from the bottom. But look on the right side. Notice how those pebbles move faster in the expanding region than the ones that are coming straight down. And you can see those gray lines that have moved faster. As you get to the constant area region, note that the gray stripes all have the same shape, which indicates that the whole bed is moving in plug flow. And then as you get to the converging region, the opposite thing happens, and the pebbles that are on the inside move the fastest, and the pebbles on the outside are the ones that move the slowest. Being able to understand how fuel moves is really critical. And we've been able to make advances in understanding these kinds of granular flows and in simulating them. This is a very, very heavily studied field of science, because if you think about it, grain silos, avalanches, sand heaps. There's all kinds of situations where we care about how granular materials move and flow. And the same thing applies if we're going to be using pebble fuel in reactors. So what we did was to design a new experimental facility that allows us to do 3D X-ray tomography of packed beds of pebbles. And the types of pebbles that we're using are the same size. These are polypropylene, but they have embedded in them a 0.3 millimeter diameter tungsten wire.
Oh yeah, I see that. There's a little wire in there.
And with X-rays, we can readily image these wires, and by observing how they rotate as they move, we can actually track thousands of pebbles, centroids, and rotation. Because if you think about it, the rotation is going to be as important in affecting how the bed moves as just the translation as well. Mm-hmm. So using these instrumented pebbles in this facility here, which we call X-Preps, and if you take a look inside,
This I have not seen.
that test section there, the conical one, is designed to match the geometry of the new Chinese TMSR-SF test reactor. Mm-hmm. And so we'll be able to do the entire core of that test reactor in terms of pebble locations and pebble motion during fueling and defueling. And also that means it's possible to do all the neutronic and thermal hydraulic simulation using realistic core geometry with real random packed
Which
pebble
is really
beds.
challenging for pebble beds.
Which is challenging, although our models are getting so much better that in fact we may have better control over where fuel is in a pebble bed almost, and control over how coolant flows than we can get with fixed fuel. Because fixed fuel has its own set of uncertainties about the geometry of the system, right? Because the subchannels, all of the spacing of all the rods and stuff is not perfectly uniform. So the ability to do the X-ray tomography, we've been studying a wide range of different fundamental geometries. This, for example, is just a converging slot where the bed comes together and then it goes into a slot. We've also been looking at experiments where we insert a blade into the bed itself and the control blade that we can use for reserve reactivity shutdown. And we can actually observe how the pebbles get pushed away at the end of the blade.
Wow.
And how it inserts and measure the forces. So this has allowed us to validate simulation models for these for these pebble bed reactors, and ultimately I think increases the confidence that we can use pebbles as fuel. And pebbles are very interesting because if you're going to refuel a solid fuel reactor, actually it's the same thing applies for the fluid fuel, but we're getting closer to fluid fuel. When you change your fuel type in a light water reactor, it's a huge deal. You have to get the new vendor to design, and you have to figure out the compatibility of the new fuel assemblies with the old fuel assemblies and how you're going to shuffle them, and then the fuel will stay for 3 refueling cycles before it's fully spent. It's very complicated. When you start looking at online refueling with pebbles, you can just put in a few pebbles to test. Once you verify that the new pebble design that you have is working, you can start to just substitute, because it's a homogeneous bed, new stuff.
Are wind and solar power the answer to our energy needs? There's a lot of sun and a lot of wind. They're free, they're clean, no CO2 emissions. So what's the problem? Why do solar and wind combined provide less than 2% of the world's energy? To answer these questions, we need to understand what makes energy, or anything else for that matter, cheap and plentiful. For something to be cheap and plentiful, every part of the process to produce it, including every input that goes into it, must be cheap and plentiful. Yes, the sun is free. Yes, wind is free. But the process of turning sunlight and wind into usable energy on a mass scale is far from free. In fact, compared to the other sources of energy, fossil fuels, nuclear power, and hydroelectric power, solar and wind power are very expensive. The basic problem is that sunlight and wind as energy sources are both weak, the more technical term is dilute, and unreliable, the more technical term is intermittent. It takes a lot of resources to collect and concentrate them, and even more resources to make them available on demand. These are called the diluteness problem and the intermittency problem. The diluteness problem is that, unlike coal or oil, the sun and the wind don't deliver concentrated energy, which means you need a lot of additional materials to produce a unit of energy. For solar power, such materials can include highly purified silicon, phosphorus, boron, and a dozen other complex compounds like titanium dioxide, All these materials have to be mined, refined, and/or manufactured in order to make solar panels. Those industrial processes take a lot of energy. For wind, needed materials include high-performance compounds for turbine blades and the rare earth metal neodymium for lightweight specialty magnets, as well as the steel and concrete necessary to build structures, thousands of them as tall as skyscrapers. And as big a problem as diluteness is, it's nothing compared to the intermittency problem. This isn't exactly a newsflash, but the sun doesn't shine all the time, and the wind doesn't blow all the time. The only way for solar and wind to be truly useful would be if we could store them, so that they would be available when we needed them. You can store oil in a tank. Where do you store solar or wind energy? No such mass storage system exists. Which is why, in the entire world, there is not one real or proposed independent freestanding solar or wind power plant. All of them require backup. And guess what the go-to backup is? Fossil fuel. Here's what solar and wind electricity look like in Germany, which is the world's leader in renewables. The word erratic leaps to mind. Wind is constantly varying, sometimes disappearing completely. And solar produces little in the winter months when Germany most needs energy. Therefore, some reliable source of energy is needed to do the heavy lifting. In Germany's case, that energy is coal. So, while Germany has spent tens of billions of dollars to subsidize solar panels and windmills, fossil fuel use in that nation has not decreased, it's increased, and less than 10% of their total energy is generated by solar and wind. Furthermore, switching back and forth between solar and wind and coal to maintain a steady flow of energy is costly. Utility bills for the average German have gone up so dramatically that energy poverty has become a popular term to describe those who cannot pay, or who can barely pay, their electricity bills. If those bills one day go down, the reason will not be more solar and wind energy, but lower oil and coal prices. There's no free lunch, and there's no free energy, and that very much includes the highly expensive energy from the sun and the wind. I'm Alex Epstein of the Center for Industrial Progress for Prager University.